I'd like to thank the organizers and TUFIC for the opportunity to speak to you today. I want to tell you about these sharp lower bounds. This is joint work with Sasha Kostochka and his student Zimu Shang. And these slides and paper are available at my website, and the paper appeared earlier this year in Journal of Graph Theory. So let's begin with the context of what we're talking about. I'll be interested in bipartite multigraphs. So I have parts X and Y covering the vertices that are independent sets, and I may have multiple edges. So I'll call this an XY bigraph. An X matching will be a matching that covers all the vertices of X. And when I have a subset of the vertices, I'll use delta sub S to mean the minimum of the degrees of all the vertices in S. Now, the famous condition that underlies this area is Hall's condition for part X, which says that for every subset of X, the number of vertices in Y that have neighbors in S is at least the size of S. And the famous result by Philip Hall in 1935 is this obviously necessary condition is also sufficient for G to have a matching that covers all of X. Now later there was an enumerative version of this by Marshall Hall, saying that if we have a simple XY bigraph, no multiple edges, then there will be a lower bound on the number of X matchings if every vertex in X has degree at least K, and Hall's condition holds for X so that there's at least one matching, then the number of matchings covering X is going to be at least K times K minus 1 and so forth, the falling factorial, till we have either K or size of X factors. And this lower bound is sharp by the example of a complete bipartite graph. Now, there's also a result when we talk about multigraphs. Igorchev and Falikman proved what had been known as the van der Waerden conjecture, although van der Waerden claimed never to have conjectured it, that if we have a K-regular bipartite multigraph, every vertex has degree K, with n vertices in each of the parts, then there will be at least n factorial times K over n to the n perfect matchings that cover all the vertices. And this is also sharp. And our goal here is to enlarge the graph context of where we have this lower bound to the setting of multigraphs, and to enlarge the multigraph context by weakening the condition of regularity to a condition where we're interested in just minimum degree of the vertices in X. Okay, so let me tell you first our main result. We're going to let capital phi of X be the number of maximum matchings in our multigraph G, sorry, phi of G. And here's the theorem. So if we have an XY bigraph, there are n vertices in X. Every vertex in X has degree at least K, and every vertex in X has at least R neighbors. Remember, we're allowing multiple edges. Then the number of maximum matchings is going to be at least R factorial times K minus R plus 1 if n is at least R, and a little bit more complicated looking formula if n is at most R. And these bounds are sharp in all cases. So some comments. You can look at any XY bigraph now and figure out what the minimum degree is in X and what the minimum neighborhood side is for vertices in X. And this theorem will give you a lower bound on the number of maximum matchings. The two formulas are equal when n is equal to R. If n equals on R, then this is R minus 1 factorial, and you multiply by r over here, you get the r factorial in both cases, and we'll get k minus r plus 1. When k is equal to r and Hall's condition holds, then the formula just reduces to Marshall-Hall's formula. Then we have r factorial if n is at least r, and this term goes away when k equals r, when n is at most r. Again, we'll get the falling factorial that Hall's condition, Marshall-Hall's formula was providing. Another interesting thing to note is when you start to make the size of x very large, but you keep these conditions the same, the lower bound on the number of maximum matchings doesn't increase, doesn't depend on n at all, which is perhaps a little surprising. Later in the talk, I will talk a little bit about stronger lower bounds that we can get when we impose various additional restrictions on the multigraph. But for now, what I'd like to spend most of the talk doing is proving this theorem for you. But first, let me give you sharpness constructions. So remember, we'll have n vertices in X, each of which has degree at least k and has at least r neighbors. So what we're going to start with is a complete bipartite graph with n vertices in X and r vertices in y. So every vertex will already have at least r neighbors. And then what I'm going to do is add k minus r copies of the edge from xi to y1 for each I. So I get multiple edges for all these edges here. This is a situation when n is less than r. This is a situation when n is bigger than r. This will be my entire graph in the case when n is at most r. But when n is bigger than r, I'm going to add the edges going straight across. I didn't have any edges incident to these vertices before that I'm adding now. So when I is bigger than r, I'm going to add the edge xi, yi. And that's going to be my construction. So let's think about how many maximum matchings there are. Note first, there are x matchings. In other words, I can cover all the vertices of x. So if n is less than r, I'll have two types of matchings. Matchings that use y1 and that don't. The ones that don't, well, I just have a complete bipartite graph n and r minus 1. And the matchings there will be r minus 1 times r minus 2 and so forth. We just pick neighbors for x1 through xn among these. Okay, so that brown formula is the number of x matchings that avoid y1. If I'm going to use y1, well, there are n times k minus r plus 1 edges incident to y1. I can pick any one of them. And then I cover the rest of x in, I have r minus 1 to choose from here. So it'll be r minus 1 times r minus 2 till I get n minus 1 factors. So in this case, I add together the brown type of matchings and the blue type of matchings. I get all the matchings, and I have the common factor here, this falling factorial, which I pull out, which leaves me an r from here, and this other factor from here. And when I add together those two factors, I get this factor. So I get precisely the formula up here that I said would be the minimum when n is at most r. It's even easier when n is at least r, because these edges that I added have to appear in every x matching. So their function is actually to restrict the choices that we have, because then what I have to do to finish up Well, the rest of these, where am I? Again, I will have to have a perfect matching, so I can pick the ways to match y1 to one of the remaining x1 through xr in r times k minus r plus 1 ways. And then to match the remaining vertices, I'll just have r minus 1 factorial choices. The rest of x will have to match into y2 through, actually, this should be yr here. So I'll get r times r minus 1 factorial times the k minus r plus 1, again, is precisely the formula up here. Okay, so we have these sharpness constructions. And now I want to prove for you that I always get at least that many maximum matchings. So I'll need a key lemma here. So let G sub n, k, and r be the set of xy bigraphs that satisfy Hall's condition and have n vertices in X with degree at least K and at least R neighbors. Okay, so I'm restricting here the graphs that I'm looking at by requiring that they satisfy Hall's condition. So for any set S, I can talk about an S matching being a matching that covers S. So here's the lemma. I'm going to fix a value R that's at least 2. So I'm cheating a little bit here in that I'm only going to prove the theorem for you when R is at least 2. R equals 1 is similar, but there's some technical differences. I want to prove that there's some graph in this family G n k r that minimizes the number of maximum matchings, and every vertex in X will have degree exactly K. It'll have exactly R neighbors. And the distribution of those incident edges, there'll be one with multiplicity K minus R plus 1, and the others will all be simple edges, just a neighbor by one edge. So first, it's easy to reduce to having degree K at every vertex of X, because we can delete a copy of an edge if we have degree more than K. We can delete a copy of an edge at X that has maximum multiplicity and is not in all of the X matchings, because either we have excess neighbors or excess degree, and deleting edges can't increase the number of maximum matchings. So, okay, we can assume that everybody has degree K. So now the idea is that if we're given a graph like this, we want to find a new graph that's also in the family that has at most as many maximum matchings as we had before. And these maximum matchings will all be X matchings because I'm assuming we satisfy Hall's condition. So I will not increase the number of maximum matchings, and I will enforce all the other desired properties up here. So it's trivial when n is 1. When n is bigger than 1, there are two cases to consider. And these two cases show up in many discussions involving Hall's theorem. Either there's some subset of X where the number of neighbors is equal to the size of S, or for every non-empty proper subset of X, we have excess neighbors. And we're going to call this case 2 property being X surplus. So let's consider case 1. We have some set S. The number of neighbors is equal to the size of S. So here's what the multigraph looks like. Here's S, the same size for the neighbors. The subgraph induced by S and its neighbors we'll call G1. The subgraph induced by the remaining vertices we'll call G2. Now, to make a maximum matching, which is going to be an X matching because Hall's condition holds, we have to pick a matching that covers X in this subgraph and a matching that covers the rest of X in that subgraph. So it'll just be the product of these two numbers of matchings. Now, since G1 has all the edges as X at S, but a smaller number of vertices than G, we can assume that each vertex of S already has all the properties we were claiming, we were seeking by the induction hypothesis. So what about a vertex down here in this part? Well, let's fix on a particular edge incident to X that appears in some X matching. We're going to keep the X matchings that use this edge and get rid of all the other X matchings that might not use that X. They cover X in some other way. So the number of edges, the number of maximum matchings of G2 won't get any bigger. So the idea is we take all the edges that were incident to X and we replace them, keeping the one copy of XY, by K minus R plus 1 edges to one vertex in the neighborhood of S, and one edge to each of R minus 2 other vertices in the neighborhood of S. So if we do this, then we'll get exactly what we wanted for X. It'll have exactly K incident edges, exactly R neighbors, all by single edges except for one vertex where we pile up K minus R plus 1 edges. Now, none of these will be in a maximum matching because the vertices in the neighborhood of S all have to be matched to vertices of S. So we will not have increased the number of maximum matchings, and we are able to make this change. Why? Because every vertex in S has at least R neighbors, so the size of the neighborhood is at least R, and R is at least 2. So we are able to make this change. Okay, so if we do this for each vertex down here in X minus S, we'll obtain this desired multigraph G prime that has all the desired properties and no more matchings. What about the case where G is X surplus? Well, the nice thing about an X surplus graph is that every edge is in an X matching, because when you delete its two endpoints, Hall's condition will still hold for the remaining graph. So here's our multigraph. Again, because R is at least 2, when we look at a particular vertex X, we have at least 2 neighbors. And now let sigma be the number of matchings in G minus X and Y. In other words, that's the number of matchings in G that contain the edge XY. And sigma prime be the number of matchings that contain the edge XY prime. So by symmetry, we can assume that sigma is at most sigma prime. And what we're going to do is get our new graph G prime by shifting all the copies of XY prime to become copies of XY. Now, if X already has only exactly R neighbors, then I'll need to leave one copy here. If I moved Q copies of the edge, then that will reduce the number of maximum matchings by Q times sigma prime minus sigma, because we're losing matchings that contained an edge here and gaining matchings that contained a copy of the edge over there. And we assumed this sigma was at most sigma prime. So if X didn't already have the desired property, then we can pick neighbors Y and Y prime so that both of those edges are multi-edges, or X had an excess neighbor. And so we are able to make this shift while still staying in the family G sub n, k, and R. Okay, so as long as the graph remains X surplus and some vertex of X doesn't have the desired properties, we can make this change. This doesn't result in any sort of cycle because the sum of the squared multiplicities of the edges increases when we do this. So we will end. And how can we end then? Either every X has the desired properties, or we reach a graph where case 1 applies. Okay, so that proves the key lemma, which is good. And now let's see how we use it to prove the theorem in the case, as I said, when R is at least 2. So we're fixing K, R, and N. The degree always has to be at least the number of neighbors. And we're in this family where X has N vertices, all of which have degree at least K and at least R neighbors. And we want to prove that there will be at least this many X matchings. Now, I already showed you the sharpness constructions. Our proof will be by induction on N plus K. K has to be at least R. When K is equal to R, both formulas reduce to the formula that was in Marshall Hall's result. Namely, this becomes R factorial, and if N is at most R, this term goes away completely, and we obtain the falling factorial from R till we get N terms. Okay, so also when N equals 1, N is at most R then, and the formula just turns into K, which is obvious because we only have one vertex to cover and we have K edges there. So again, we're going to run into these two cases that we had in the lemma. If we have case 1, we have this set S, whose neighborhood size is the same as the size of the set. Again, we have G1 and G2. We break up the graph as we did before. And because all the edges incident to vertices of S are in this subgraph G1, G1 is in this family where we have size of S vertices in the first part. Again, degree at least K and at least R neighbors for each of them. So we can apply the induction hypothesis. An X matching will have to send S into its neighborhood and X minus S into Y minus the neighborhood. And the number of matchings that send S into its neighborhood will be, by the induction hypothesis applied to G1, exactly R factorial times K minus R plus 1. Because the size of the neighborhood has been assumed to be at least R, which is the same as the size of S, and S is smaller than the full set X. So we're in the case where N is at least R, so we can apply, in this case, the size of S is at least R, we can apply the first case of the formula. And that's good enough because we know that there is at least one matching from X minus S into the remaining vertices of Y. Okay, so that's easy. But the interesting thing happens when we look at case 2, where G is X surplus. Again, we looked at the base case K equals R, so we may assume K is bigger than R. And we can assume that our minimizing example G has the properties as in the derived in the lemma. So that means that for each vertex of X, there's one incident edge that occurs with multiplicity K minus R plus 1. And I'd like to give a shout out to Zimo Xiang here, because it was his observation that we can handle this by deleting one copy of each of those edges. So each vertex of X is going to lose one edge, but it won't lose any neighbors because K minus R plus 1 is at least 2. So this new graph that we get by deleting those edges will be in this special family where, again, Hall's condition holds. We have N vertices in X. Each has degree at least K minus 1, actually exactly K minus 1, and it has R neighbors. So we can apply the induction hypothesis to G prime. If N is at least R, we'll have R factorial times K minus R X matchings. And if N is at most R, we'll again have this ugly looking formula where we replace the K by K minus 1. So what we need to do is gain some more X matchings using the edges we deleted. We need R factorial more if n is at least r. And we need to change this k minus 1 into a k. So we need this many more if n is at most r. Well, because G is X surplus, deleting the endpoints of any edge from G prime leaves Hall's condition. And we might lose one neighbor from the vertices, but at least we're going to have r minus 1 neighbors left. So what that means is if we look at the underlying graph, every edge of G prime lies in at least Q X matchings, where Q is this formula that comes from Hall's result. Again, a falling factorial. So we can use one of the deleted edges instead. And there will be exactly, or at least rather, Q X matchings that use exactly one of those deleted edges. And that's true for each of those deleted edges. And we deleted one from each vertex of X. So that means we'll get at least n times Q distinct matchings, X matchings in G that don't lie in G prime and use just one of our missing edges. But that's exactly what we need. Look at Q. Q is here. If n is at most r, Q is exactly this falling factorial, and we get n times Q, that's exactly how many we needed. And if n is bigger than r, well, then we get n times r minus 1 factorial is what Q is, which is at least r factorial, bigger than r factorial. So that actually completes the proof of the theorem. Well, except I was assuming Hall's condition. So I was assuming there was an X matching. And I need to prove for you what happens when there is no X matching. So let's let alpha prime be the maximum size of a matching in G. And what I want to show you, since I proved the lower bound only when alpha prime is equal to the size of X, I want to show you that when alpha prime is smaller, in fact, we get a better lower bound. Okay, so this is what I just said. When alpha prime is smaller than X, I want to show you that the lower bound is even bigger. So here's the corollary. If I have an XY bigraph, n vertices in X, every one of them has degree at least K and has at least R neighbors. Maybe I don't have an X matching. Let's let P be the number of vertices lacking when I take a maximum matching. Yeah. And if P is bigger than 0, then I claim that the number of maximum matchings is going to be at least R plus P factorial over P factorial times K minus R plus 1. Now remember, when P is 0, this just reduces to R factorial times K minus R plus 1, which is the formula we had before. And if we replace that R factorial by, okay, R plus 1 over 1, R plus 2 over 2, the number is getting bigger. Okay, this factor will be bigger than R factorial. So to prove this, I use what is a very common trick in generalizing results about matchings. I'm going to form a new multigraph G prime by adding P vertices to the set Y. And I make each of those vertices adjacent by an edge of multiplicity 1 to all of X. Okay, so what does this do? Well, excuse me. Each maximum matching in G can be extended to an X matching in G prime, because the P vertices that were unmatched can be matched to the added vertices in Y in any order. So I get P factorial X matchings in G prime out of every maximum matching in G. And furthermore, every X matching in G prime arises in this way because all these edges, all these vertices of X are matched, and we have to use the P new vertices. So, so any X matching in G can be obtained in this way. What that means is that the number of maximum matchings in G is exactly the number of maximum matchings in G prime, these will be X matchings, divided by P factorial. Well, we can apply our theorem to G prime, because for every vertex of X, we've increased the neighborhood by P vertices, we've increased the degree by P edges. So that means G prime is in this family we were talking about with parameters n for the size of X, K plus P for the degree, and R plus P for the number of neighbors. And furthermore, alpha prime will have to be at least R. You can get a quick contradiction if it's not. And so we apply the case of the theorem where n is at least the neighborhood parameter. We get R plus P factorial times K plus P minus R plus P plus 1. Well, this formula, P's cancel out. It simplifies to up here because we have to divide by P factorial. So that proves the corollary. Okay. So, I've proved the main result for you completely in the case that R is at least 2. And now I want to spend some time showing you some sharpness examples for other results. So let's think about adding constraints on Y. Well, if you remember the sharpness example that gave this many X matchings when n is bigger than R, which was independent of n, we had these edges going straight across here. So you can notice two things about this construction. One is that we have vertices of degree 1 in Y, and another is that Y has the same size as X. And in fact, even when we only have the condition R equals 1, you see here's this vertex X1 has only one neighbor, Y1. Then we had this construction. I want to focus on this guy because I'm going to use him several times. So we have HNK, we had 4 vertices over here, and everybody has degree at least 3. And there is a maximum matching that covers X. So here I've used 1 copy of each xi, yi, and k minus 1 copies of plus k minus 1 copies joining each vertex to y1. And here's a slight modification of that, where I made all these guys y2 through yn adjacent to xn. I did that in order to bump up the degree of vertices in y to 2. Now, if you count the maximum matchings in this graph, or in this graph, you have to match everybody straight across. So the only choice here is one of these k edges. And the same thing happens in this graph. You have to match everybody straight across. You can choose one of these k and one of these 2. So there are that many x matchings in this new graph here. Well, these are in fact sharpness examples. If we have an XY bigraph, minimum degree at least 3, and the size of X is at least 3. If we require vertices in Y to have degree at least 2, or the size of Y to be bigger than the size of X, then every such example is going to have at least 2 K maximum matchings. So this is a sharpness example. There's one exception. This graph, when K and X are both 3, has 5 matchings instead of 6, 5 X matchings. Now, this looks like a rather mundane little example here that is not very interesting, but it's actually a special case of something more general. Namely, let's talk about what we can do if the size of y is bigger than the size of x. Let's start with this example that we've been talking about. Here are 2 copies of it. And I'm going to add, but starting with only n minus 1 vertices in x. I'm going to add 1 vertex to x to get up to n. And I'm going to add t plus 1 vertices in y so that the size of y will be t bigger than the size of x. Okay, now let me make x n adjacent to everybody in y. Okay, so that's the construction here. And for this example, because I want this degree in y to be at least 2, I'm going to add 2 edges joining x to each vertex of y. Well, if you count the maximum matchings, again, x has to match straight across, so there'll be a factor of k there. And everybody has to get matched straight across, and we're left with a choice of matching xn to one of the t plus 1 new vertices. So I get k times t plus 1 x matchings in this example, 2k choices for the last edge times t plus 1 x matchings in that example. And once again, now that I've allowed y to be bigger than x, these are sharpness examples. Every vertex in x has degree at least k, and the size of y minus the size of x is t. Then if the minimum degree of y is at least 1, I'm going to have at least this many x matchings. And if the size of y is degree in y is at least 2, then at least twice that many. So we've proved this theorem also, and these are sharpness examples. Again, there's one exception. This example over here, n and k are 3, but it has 11 x matchings instead of 12. Okay. Now we get to something more substantial when we talk about x surplus graphs. Again, an xy bigraph is x surplus if every non-empty subset of x, proper subset of x, has excess neighbors. In such a bigraph, every edge lies in an x matching. And this property, these families, were studied by Lovas and Plummer in 1986 and by Liu and Liu 2004. They were called elementary graphs or positive surplus graphs without the restriction to bipartite graphs. So when we restrict to bipartite graphs, bipartite multigraphs, we're calling this X surplus. The interesting thing now is if we require that every vertex has at least 2 neighbors, then the number of maximum matchings is suddenly going to have to grow with the number of vertices in X, the difference between the size of Y and the size of X, and the number of edges in the graph. So this is quite a surprising change compared to the sharpness examples I was showing you before, where the results did not grow with n or the number of edges. So here's the theorem that we proved. If we have an X surplus XY bigraph, every vertex has at least 2 neighbors, n vertices in X, the difference between the parts is t vertices. And now, because every vertex has a degree at least 2, we have to have at least 2 times the size of Y edges. And then if I subtract that from the number of edges in the multigraph, I get a quantity I'll call B is the number of excess edges in some sense over the minimum that's required. Then we prove that the number of maximum matchings has to be at least n minus 1 times t plus 2 plus b, all times t plus 1. So it grows quadratically in the difference between the sizes. also grows with a factor of n here, also grows a little bit with each added edge. And the surprising thing is that this lower bound is sharp in all cases. Okay, it looks a little complicated. I'm not going to prove this result for you because it takes us 10 pages to do it. But I do want to show you a sharpness example. So, oh, yeah, let me comment that actually the case with t equals 1 was proved by Liu and Liu in the case of simple graphs, and the case t equals 0 follows from the results of Lovas and Plummer, that our proof takes care of these cases independently. So here's a sharpness construction. I'm going to start with a cycle of length 2n. This already, if these are my n vertices in X, this already makes the graph X surplus. I'm going to add t more vertices. They will all be copies of the vertex yn. So they all have these red edges, the same two neighbors that yn has. So notice that every vertex in y now has degree 2. That's the requirement we were expressing, and we're going to have b extra edges. So I'll add b extra copies of the edge from n to y1, xn to yn. Now this is my whole example, my construction. I want to show you that it has precisely the number of X matchings that's in that formula. Well, as I noted, the graph is X surplus and everybody has at least 2 neighbors. So there are a couple kinds of X matchings. Suppose first that we use 2 of the red edges. So xn and xn minus 1 are both matched to these guys here. Well, there are t plus 1 times t ways that we could match these two into those t plus 1 vertices using red edges. And once after we do that, we have to match the rest of x1 through xn minus 2 along this path. And that's just determined by which vertex of y1 through yn minus 1 we choose to leave out. So for each of these t plus 1 times t pairs of edges, we can finish the matching in n minus 1 ways. Okay. So the other kinds of X matching will use one edge, one red edge. If I cover xn with a red edge, there are t plus 1 ways to choose it. And then, since I'm not using a red edge at xn minus 1, everybody else matches straight across. So that's 1 times t plus 1 matchings. If I don't use the red edge at xn, then I have to match xn by using one of these blue edges, and there are b plus 1 blue edges. And I'll use my red edge for xn minus 1. Again, t plus 1 ways to choose it times b plus 1. So b plus 1 times t plus 1. So I have these 2 types of edges, and when I add them together, 2 types of X matchings, when I add them together, I get precisely that formula that was on the previous slide. Okay, so this is a sharpness construction. So as I said, I'm not going to prove this result for you. Oh, right. So I have a little bit of time left. Let me mention a couple of open problems. What is the minimum number of maximum matchings when we have an XY bigraph that has an X matching? Every vertex in X has degree at least K. Every vertex in Y has degree at least S. Well, I've already talked to you, so here's another reason why I showed you those examples when the degree in y was 1 or 2. We know the answer to this question when s is 1 or 2, when in the case where x is at least 3 and k is at least 3. So is it true in general that it would always be at least s times k when s is bigger? We don't know. There's an open problem for you. Another open problem, what is the minimum number of maximum matchings when we have an XY bigraph? That's X surplus, with the difference between the parts being T vertices, and every vertex having at least R neighbors. So the theorem I didn't prove for you said we know the answer to this when R is 2. We also know the answer in the non-X surplus case. I want to save a little time, so I won't read this for you. But again, we do know the answer in the non-X surplus case. And in the X surplus case, when R equals 2,
We have 5 minutes more, so it's okay.
Yes, yes, but I want to tell you something else.
Okay, great.
For the X surplus case, when R equals 2, that long theorem, well, it takes long to prove it, and gave us this as the minimum number of X matchings. Okay. So what about when R is bigger than 2? Well, we don't know the answer, but let me show you a construction. Here's a construction. Now, this looks very ugly, maybe, but it's beautiful, believe me. So the heavy edges here are complete bipartite subgraphs, okay? And between T and T prime, I have just a matching going straight across, okay? U and U prime are just single vertices there. Now the dashed line here means I can add any edges that I want, including multiple edges, but joining S and S prime. Okay, the other stuff is all simple edges. Now, we can compute exactly the number of maximum matchings in this graph. Actually, it's X surplus, so they are all X matchings. And here's the formula. Now, that looks really horrible, but it's not. Let me just hint to you what's going on by counting the X matchings if I add some edge here and want to use that edge. If I want to use that edge, then between U prime and S prime, there will only remain R minus 1 vertices available. And all the vertices of R will have to get matched into those. And it can do it in R minus 1 factorial ways, because you're matching R minus 1 to R minus 1. But with all of S prime now used up, the vertices in T must match straight across. So there's only one way to do that. So to complete the matching, you will have these R vertices from S and U have to match up here to these T plus R minus 1 vertices, and that's where you'll get this falling factorial. So any edge that you add between here will belong to exactly that many X matchings. So that's all the extra edges, this B, will all give you that term, okay? And these other terms, there are a few other ways you can make X matchings without using any edges going across here, and they give you these contributions. Now, the interesting thing about this construction is what happens if we set R equal 2? Well, this becomes 1 factorial, this becomes T plus 1, this becomes n minus 3 times T, and here's another 2 times T. So lo and behold, the formula reduces to exactly the result that is the minimum when R equals 2. So is this a sharpness example? Well, we don't know, but it reduces to a sharpness example when R equals 2. So maybe someone else can finish this up for us. This, I think, is a tantalizing sort of question. Okay, so I'm out of time, and thank you for your attention.